Lesson 5, Effective Value and Circuit Elements. Section 5.2, Resistance. Ohm's law states that V equals Ri. Resistance is the ratio of the voltage V to the current I. The unit is ohm. If the voltage V is a sinusoidal voltage expressed as V equals Vm sine omega t, then I equals V over R, equals Vm over R sine omega t. There is no phase shift between V and I. Section 5.3, Inductance. Inductance is the ratio of the induced voltage V to the derivative of the current I with respect to time t. The inductance is denoted by L. The unit of inductance is Henry. If the voltage V equals Vm sine omega t, then the current I is derived as I equals 1 over L, times integra V dt. By replacing V with Vm sine omega t, I becomes Vm over L, times integral sine omega t dt. The integration of sine omega t is obtained as negative 1 over omega, times cosine omega t, therefore, I equals negative Vm over omega L, times cosine omega t. Negative cosine omega t equals sine omega t minus pi over 2, thus, I equals Vm over omega L times sine omega t minus pi over 2. The current I, which flows into the inductance, lags the voltage V by pi over 2. When performing indefinite integration, an integration constant is always included. For inductance, this integration constant corresponds to the initial current. When conducting a steady-state analysis, the transient phenomena resulting from the initial current are ignored. This is because the focus is on the long-term behavior of the system, after any transient effects have dissipated. Experiment 5.3. Construct this circuit. Set the source voltage V equals Vm sine omega t, where the amplitude Vm equals 4 volts, and the frequency f equals 10 kHz, and 20 kHz. Measure the voltage across the resistor VR, and the voltage across the inductor VL. Find phi, where phi is the phase shift of I relative to VL. The answers to experiment 5.3. Connect the 1+ pin to the top of the RL circuit, and the 1- pin to the point between R and L. This makes channel 1 of the oscilloscope measure the voltage across the resistor VR. These are the measured waveforms. The orange line represents the voltage across the resistor VR, and the purple line represents the voltage across the inductor VL. This is the case where the frequency f was 10 kHz. The horizontal axis is 10 microseconds per division, and the vertical axis is 1 volt per division. The period t of these voltages was 100 microseconds. The time shift between VR and VL was 25 microseconds, and it was t over 4. The current I is proportional to the voltage across the resistor VR due to Ohm's law. Thus, the waveform of I is proportional to that of VR. Let's use radian as the unit. Then, the phase shift phi of the current I, relative to VL, was negative pi over 2. The current I lagged the voltage VL by pi over 2. The figure on the right shows the waveforms for f was 20 kHz. The horizontal axis is set to 5 microseconds per division. In this case, the phase shift phi was also negative pi over 2. Exercise 5.3. This is the experimental circuit from the previous experiment. Assume that the voltage across the inductor VL equals VLm sine omega t. Then the current I equals VLm over omega L, times sine omega t minus pi over 2. These waveforms were the results from the previous experiment. This is the case where f equals 10 kHz. Find the value of omega L, where L equals 10 millihenries. Find the amplitude of the current Im, if VLM is 2.1 volts. Find the amplitude of the voltage across the resistor VRM, using the above Im, and compare it to the reading from the waveform of VR. You can round the answers to two significant figures. The answers to exercise 5.3. Omega L equals 2 pi FL, and it is calculated to be 6.3 times 10 to the power of 2 ohms. The answer is rounded to two significant figures. Im equals VLM over omega L. And VLM is given as 2.1 volts. Thus Im equals 3.3 times 10 to the power of negative 3 amperes. According to Ohm's law, VRM equals RIM. Using the above Im, VRM is obtained as 3.3 volts. The reading of VRM from the waveform of VR is also 3.3 volts. Section 5.4, Capacitance. Capacitance is the ratio of the current I to the derivative of voltage V, with respect to time t. The capacitance is denoted by C. The unit of capacitance is farad. If the voltage V equals Vm sine omega t, then the current is derived as I equals omega C Vm, sine omega t plus pi over 2. The current I leads the voltage V by pi over 2. Experiment 5.4. Pause the video, and follow the instructions. Measure VR and VC. Find the phase shift phi. The answers to experiment 5.4. These are the measured waveforms of the voltages VC and VR. The phase shifts were found to be pi over 2, and the currents I led the voltages VC by pi over 2. Exercise 5.4. This is your homework. Find omega C, find Im. And find the voltage across the resistor VRM using Im. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.